Today I continue the story from where I left off in my previous presentation on Murphree efficiencies. Just a short recap. We consider a distillation tray with a vapor composition YE entering the tray and the composition of vapor Y sub L leaving the tray. We can define the component Murphree efficiency as the difference in the composition between the vapor leaving the tray and the vapor entering the tray divided by the composition change that can be achieved if the vapor leaving the tray were to be in thermodynamic equilibrium with the liquid leaving the tray. So physically, the Murphree efficiency is the actual accomplished change in vapor composition divided by the potential change in the vapor composition under conditions in which the distillation tray operates under thermodynamic equilibrium conditions. For a binary mixture, since the mole fractions add to unity, the Murphree component efficiency of component 1 must equal that of component 2. This equality is no longer required for mixtures containing 3 or more components. For a ternary mixture, for example, the 3 component efficiencies may differ from one another. Theoretically also, for a ternary mixture or a quaternary mixture, there is no requirement that the component efficiencies be bounded. In other words, lie between 0 and unity. In this presentation, I would like to demonstrate, firstly, that the component Murphree efficiencies for multi-component distillation are indeed unbounded and can have component efficiencies greater than unity or less than 0. Secondly, I'd like to explore the Murphree efficiency concept for liquid-liquid extraction and also demonstrate the unboundedness of the Murphree component efficiencies. Thirdly and finally, I'd like to take a sideways look at transient adsorption of binary mixtures in a zeolite and demonstrate that the component Murphree efficiencies may indeed exceed unity for kinetic separations. Let's begin the story by recapping what we achieved in our previous presentation. In my previous presentation, I had analyzed the experiments of Martin Springer carried out in a distillation column under total reflux conditions for the ternary mixture of water, ethanol, and acetone. The experimental data of Springer shows that the distillation boundary, shown by the thick black line, may be crossed. Here we show the compositions of the 11 trays in blue, ranging from the reboiler to the condenser. If the trays were to operate under equilibrium conditions, the composition trajectories must follow the residue curve maps shown in pink, and no boundary crossing is allowed if the stages were to operate under thermodynamic equilibrium conditions. The actual conditions, we note that as we move up the column from the reboiler to the condenser, the compositions cross the distillation boundary. To explain and rationalize the boundary crossing effect, we had set up a simple model for the distillation tray in the Springer experiments. The bubble froth regime is described by bubbles of uniform size of 4.5 millimeters, rising at a velocity of 20 centimeters per second, leading to a vapor-liquid contact time of 46 milliseconds in the froth height, which is estimated to be 9.2 millimeters. Using the Maxwell-Stefan diffusion equations for ternary gas mixtures, the Geddes equation, represented here, which represents the unaccomplished change divided by the potential change. Indeed, the Murphree efficiency is 1 minus this quantity. This can be solved, can be even solved analytically, can be solved numerically for the bubble dispersion on the tray, and the composition trajectory followed during the equilibration process as the vapor traverses the height of the dispersion froth can be calculated. The Maxwell-Stefan model calculations for a typical tray with a feed composition entering the tray somewhere here, and this is a blown up diagram showing the compositions. This is the entering vapor composition. The Maxwell-Stefan model calculations are shown in blue as it traverses the tray. For a contact time of 46 milliseconds, the compositions have attained or achieved boundary crossing. If the tray dispersion height were to be tall enough such that the vapor bubbles could equilibrate, then the compositions would get back to the position shown here, and no boundary crossing would be observed. In other words, the Maxwell-Stefan model anticipates a scenic route to equilibration, and since the equilibration is stopped before thermodynamic equilibrium can be achieved, we have the phenomena of boundary crossing. We can determine the component efficiencies of each of the three components, and we note that the efficiency of water is significantly larger than the efficiencies of ethanol and acetone, and the differences in the component efficiencies drive the compositions during the equilibration trajectory away from the path dictated by the residue curve maps shown in pink. So put another way, differences in the component efficiencies cause boundary crossing. That was the conclusion drawn in my previous presentation. Let us examine now another set of experiments carried out by Springer in his PhD dissertation. This is for a quaternary mixture of water, ethanol, methanol, and acetone. The experimental data are plotted using these blue circles in ternary composition space, where the compositions of methanol and acetone are combined. This is the distillation boundary, and again we note that the experiments show the phenomena of boundary crossing and the acetone boundary has been crossed. If we take a vapor composition entering the tray somewhere here in one of the stages, and the Geddes model combined with the Maxwell-Stefan diffusion equations, the transient equilibration trajectory followed by the vapor bubbles are shown by the blue lines that indicate boundary crossing phenomena. And we note again that rather than follow a straight line path, the equilibration trajectory is curvilinear. And the component efficiencies are calculated from the simulated trajectories, and the component efficiency for methanol for a range of Fourier times exceeds unity. So we have the demonstration of the unboundedness of the Murphree component efficiencies. One of the components may have efficiencies exceeding unity. And this deviation of the component efficiency from unity values contributes to the boundary crossing for this quaternary mixture. Moving on to the ternary mixture water, ethanol, tertiary butanol. This is a system also with a distillation boundary, and these are the calculations using the Maxwell-Stefan Geddes model, starting with a vapor composition entering the tray. The blue line shows the equilibration trajectory as it rises to the through the dispersion froths. And as is to be expected, the equilibration trajectory follows the scenic route to equilibrium and not the straight line path. And the component efficiencies calculated on the basis of the equilibration trajectory are shown here. And particularly noteworthy is that the efficiency of tertiary butanol is negative for a range of contact times. The negative efficiency of tertiary butanol has been experimentally confirmed in this paper published in 1977, carried out in the separations process group of George Standard at the University of Manchester. For interested readers, you may also wish to read this paper on Studies in Distillation, number 5 in Chemical Engineering Science in 1965, that lays out the standard efficiency as a more thermodynamically precise definition of the Murphree component efficiencies. This paper is of historical importance, and we will encounter the name of standard once again further down the road when we discuss liquid-liquid extraction. The message from this work is that negative efficiencies are possible and can be routinely calculated using the Maxwell-Stefan diffusion equations, along with a mass transfer model such as for bubble dispersions and the Geddes equilibration trajectory. Let's move on to liquid-liquid extraction, and we draw a precisely analogous picture for mass transfer in a sieve tray column, in which the rising droplets of liquid are contacted with the continuous phase. Generally speaking, mass transfer resistances are present in both the dispersed phase and the continuous phase, and both these resistances can be routinely accounted for. Just to be consistent, we apply the Geddes model to describe the equilibration within the droplets. We could use the Kronig-Brink model, but the results would be almost exactly the same, and the same kind of effects are observed, albeit at a different Fourier time. We examine mass transfer in the extraction of a mixture of propylbenzene and tetradecane using the solvent NMP. The feed mixture is a 50-50 mixture of propylbenzene and tetradecane, shown here. This is contacted with the solvent NMP on a sieve tray column. If we join this point with this NMP at this position here, the mixture composition ends up in the two-phase region. This will equilibrate along the tie line, shown by this yellow line, and we examine mass transfer in the raffinate phase as it moves up the column in the form of uniform droplets of liquid. Using the Geddes model for equilibration and the Maxwell-Stefan diffusion equations for this ternary mixture, we can calculate the equilibration trajectory the liquid droplets follow as they move up the tray in the liquid-liquid dispersion. The equilibration trajectory is curvilinear and does not follow the straight line path dictated by a model that assumes that the components will transfer at the same rate. Indeed, the component efficiencies for NMP, blue line, propylbenzene, red line, and tetradecane show that the component efficiencies are all significantly different from one another, and noteworthily, the tetradecane efficiency has a negative value during the initial stages of equilibration. For the liquid-liquid mixture glycerol, acetone, water, the model calculations using the Geddes Maxwell-Stefan description of a feed composition shown here. As it equilibrates to this composition, the blue line shows the calculated equilibration trajectory. This is curvilinear, and they match the experimental data published in 1985 in the standard group at the University of Manchester. The calculated component efficiencies are plotted here in this diagram as a function of the Fourier number, and we note that the component efficiency of water exceeds unity for a range of contact times, and the component efficiencies of the three species are all unequal. So the message so far is that due to coupling effects in molecular diffusion, the equilibration trajectory followed by bubbles of vapor components in ternary distillation or liquid phase components in liquid extraction. The trajectories follow serpentine paths in composition space and do not follow the straight line trajectory anticipated by a model that assumes that the component efficiencies of each species is the same. In other words, the departures from straight line equilibration is to be attributed to differences in the component efficiencies, and the curvilinear equilibration paths may cross distillation boundaries. For liquid-liquid extraction, they may also enter the metastable regions and cause emulsification. Let's switch gears and move on to binary mixture adsorption in zeolites. Let's consider the adsorption of mixtures of nitrogen and methane in LTA4A zeolite. LTA stands for Linde type A. LTA4A consists of cages of 11 angstrom in diameter, and each cage is separated from adjacent cages by windows which have an aperture of 4 angstrom, hence the name 4A. In practice, for purification of natural gas, we need to selectively remove nitrogen because the presence of nitrogen reduces the heating value of natural gas. In remote locations, pressure swing adsorption is used for the separation, and we need an adsorbent that selectively takes up nitrogen so that purified methane can be rejected and recovered in the gaseous phase. However, most known adsorbents selectively adsorb methane that has a significantly higher degree of polarizability than nitrogen. So the technological solution is to resort to kinetic separations in which we rely on separating the binary mixture by relying on the higher diffusivity of nitrogen within the pores of LTA4A zeolite. Now, nitrogen is a pencil-like molecule whose cross-sectional dimension is 3.3 angstrom, that is significantly smaller than the diameter of the methane molecule. And since the aperture is only 4 angstrom, the diffusivity of nitrogen is about 20 to 25 times larger than the diffusivity of methane. The higher diffusivity of nitrogen within the pores of LTA4A leads to higher loading of nitrogen during the transient approach to equilibration. Habgood in 1958 measured the transient uptake of a mixture of nitrogen and methane within the pores of LTA4A. The nitrogen uptake is shown by the red circles, and the green squares are the loadings of methane. Methane approaches its equilibrium loading in a monotonic manner, whereas nitrogen exhibits an overshoot in its loading as it approaches its equilibrium loading. The attainment of supra-equilibrium loading during the initial stages of the equilibration process is due to the significantly higher diffusivity of nitrogen. Indeed, the occurrence of transient overshoots is essential for this kinetically driven separation of nitrogen and methane. Let's replot this graph and calculate the component efficiencies. From the experimental data shown in the previous slide, determined by Habgood, we can determine the Murphree component efficiencies. The red circles show the component efficiency for nitrogen, and the green squares show the Murphree component efficiency for methane. We note that the nitrogen component efficiency exceeds unity for a significant range of contact times during the equilibration process. Indeed, the attainment of supra-equilibrium loadings and component efficiencies greater than unity is an essential characteristic of the kinetic separation of nitrogen and methane. The solid lines are the simulations of the transient uptake using the Maxwell-Stefan model, in which the component 3 is treated as the zeolite, which is a pseudospecies. D1 and D2 are the diffusivities of nitrogen and methane within the zeolite. The solution of these of the Maxwell-Stefan equations, along with the model for transient uptake, leads to the continuous solid lines. The details are available in the published literature. See also my presentation on transient overshoots on my YouTube channel. We move on to transient uptake of mixtures of carbon dioxide and ethane in DDR zeolite. DDR zeolite consists of cages that are separated from adjacent cases by windows that have an aperture of 3.7 angstrom in this direction and 4.4 angstrom in this direction. CO2 being a thinner pencil-like molecule, hops between adjacent cages far more quickly than its partner ethane, which is much more severely constrained in the window regions. But ethane has much stronger adsorption strengths in DDR zeolite. So we have a combination of a more mobile molecule that is relatively poorly adsorbed and a tardier molecule that is more strongly adsorbed. This combination leads to the possibility of kinetic separation and the transient uptake of mixtures of carbon dioxide and methane are shown here. The experimental data are shown by the red circles and the green squares for CO2 and ethane respectively. And the data for three particular set of compositions in the bulk vapor phase, a mixture with 20 kilopascal each of CO2 and ethane. Here we have 40 kilopascal of CO2 in the bulk vapor phase, 20 kilopascal of ethane in the vapor phase. Here we have partial pressure of 60 kilopascal of carbon dioxide in the vapor phase and 20 kilopascal of ethane in the vapor phase. In all cases, we note that the Murphree component efficiencies calculated from experimental data on transient uptake show values exceeding unity for CO2 during the initial transients before it finally reaches a value of unity when the system is fully equilibrated. The continuous solid lines are the Maxwell-Stefan model, in which the zeolite is treated as component 3, a pseudo-species in the mixture, and we note that the experimental data is very well reproduced in the Maxwell-Stefan model. Further details are available on my other presentations on the YouTube channel, which you may refer to. There are three takeaways from this presentation. Firstly, Murphree component efficiencies for multi-component mixtures are unbounded. They may have values exceeding unity or lower than 0. We've analyzed multi-component distillation, multi-component extraction, and mixture adsorption in zeolites. In each of the examples we have considered, we have the possibility of uphill transport and component efficiencies exceeding unity. We have compared experimental data with the Maxwell-Stefan model to describe the equilibration trajectory, and in all cases we note that the equilibration process follows a scenic route or a curvilinear path to equilibration. And following this scenic route to the equilibration opens up new vistas, as has been noted by William Wordsworth.